So what we're going to do now is we're going to say the following. We're going to say, how do I define my event? So the way I define my event, I have to have certain basics. I need the whole sample space there. I need all these events, these intervals. If I look at the interval example, I need contour unions, complements, everything to be there. So let's do definitions. So this definition. So this definition 5.1.1. So the term for these is called sigma field. So it's called sigma field. So the event spaces have to be sigma fields. Okay, so that's what the idea is, that one has to check that. So what does it mean? If S is a sample space, F is a sigma field on S, script F sigma field on S, is a collection of subsets of S such that what happens, three things happen. That is, one is the probability of S is, so you need S to be there, right? So in the sample space. So you need, one is that you need S to be an event. S has to be F. The second thing is, we also know that because we have probability of an event happening, then a probability of event not happening should also be there. So that means we need, if A is in F, then a complement has to be in F. That condition we will have. Very good. And the third condition we will need is that if I take any countable collection, A2 and AN, and so forth, a countable collection, so here I won't require the disjoint property. Disjoint means the probability will sum up, but I don't require that, of sets in F. Then their countable union is also in F. So that's the rule book I place on my collection of subsets that I want to play with. Very nice. So these are three rules. I have the whole set S in it. If an event or a subset A is in F, I want its complement also to be there. And if I have a countable sequence of events, I don't require disjoint. Any countable sequence, I want the union to be in my collection F. So then what we'll do is we shall refer. This is how we'll close the subject. We shall refer to an element in the sigma field F, of element of the sigma field F, as an event. So that's my event. My event is any element of the sigma field. And what sigma field? Sigma field is any collection of subsets which satisfy these conditions 1, 2, and 3. And then what we'll do is to go to our problem, to our particular problem of 0, 1. What we will do is, if S is equal to 0, 1, what we will do is we will designate our event space or what we're interested in. So the smallest sigma field that contains all intervals. So you take an interval, by the rules of the game, you need to have its complement. If you take countable many of them, by the rules of the game, you need to have the countable union to be there. For this case, so we will take the smaller sigma field that contains all intervals. So this sigma field has a name. This is called the Borel sigma field. So that will be our event space when S is 0. So it will be the smaller sigma field that contains all intervals. This will be our event space. And it's a fact, again, that I will not show. It's beyond the scope of this class. That A, let's call this as script F. A is an F. One can define length of it. Okay, this is something that you have to believe me again. I will not show it in this class, but so this is the correct collection that you should take to understand how to choose a number uniformly in zero. And the same definition will also work when S is so the same thing you will take is that same approach you will take if S is equal to R or S is any subset of R, then also we will take or designate the event space as the Borel sigma. That is the smaller sigma field that contains all intervals in S. That's one thing we will do. So that's going to be our working space now. The event space is going to be sigma fields. And then once you do this, then you're sort of in obvious territory. You have S, you have F. Then how do I define probability? So here's definition 5.1.2. So here, so I have to just define probability again. So I'll just define the probability space axioms. With this definition of event. So what I will say is let S be a sample space, F be a sigma field on S. That means F is a collection of events that has this property that if the set is there, then its complement is there. If a collection of events are there, then its countable union also is there. So a sigma field should have these properties. And for any event A, I think of my events as just elements of sigma field. So I'll define a probability on it. So what I'll do is I'll say a probability now is a function taking P from F to 0, 1 such that 1, the old axiom holds, the probability of S is equal to 1, and second as before, that if I take E1, E2, and so on and so forth, En are a countable collection. So here I will since for probability I always want disjoint elements in F. Then what I want is the probability of the countable union is the sum of the probabilities. . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . And the triplet SFP, I will always refer to it as, is referred to as probability space. Very nice. So there are two key things I'd like to emphasize again. Let me just recap this for you. So like I said, I want to understand events a little differently. So I put a bunch of rules for events. That is, if S is there, then and A is there, then A complement is there. If I have a countable collection of events, then the union is there. So that's what I call a sigma field. And I'll think of any element of sigma field as an event. Now, if I restrict myself to this class of events, which is part of one sigma field, and I take the sigma field that contains all intervals, and I take the smallest one that does that, that's called the Borel sigma field. That will be my event space for S equals 0, 1. And I'll restrict my old definition of probability to only sigma fields. I will not take the power set of S for any S. So this is the setup we will work with. From now on, events are, by events I mean I have an appropriate collection of subsets that satisfies these rules given by definition 5.1.1, and that will be my definition. That will be all my events. I'll define probabilities for all such subsets of S. So a couple of points before I go back to my experiment of picking a number uniformly in 0, 1. I still have work to do there. I still haven't gotten that. I've told you how to do events now and probabilities now. So now I have to go back and tell you just a couple of remarks. So there is no deviation as such from our previous setup. There's no deviation in our previous no deviation from our previous setup in some sense. No deviation for our previous setup. Because so note that if S is countable, then if you take the power set of S, that is a sigma. So there's no real problem. So in general, an event space can be any sigma field. When S is 0, 1, we will take the Borel sigma field, and S is R, we will take the Borel sigma field, or S is any interval, we will take the Borel sigma. So there is no. So this convention we will always do. If S is an interval AB or S is equal to R, we will always work with the Borel sigma as the events. So that's what we will do going forward. So again, a sigma field means it satisfies 3 rules, like we said. Sigma field means it satisfies 3 rules. So in this case, the Borel sigma field will be one thing. It will contain all intervals. It will contain intervals. So this collection will contain intervals. It will contain the whole set. S will be, let's call this as F. S will be there. If it will have one rule of that, if one rule, other rule is A is in F, then A complement is in F. And if there are A1, A2, AN are a countable collection of events, then the countable union is in F. So these are all in F, then countable. So what we'll do is we'll take the smallest collection that has this. So that's what we mean by the Borel sigma. It has these 3 rules, 1, 2, and 3. Very good. So an old deviation, there's no deviation from our old setup. It doesn't matter. The power set of S is also a sigma field. There's no problem. So the same definition of probability will hold, and there's nothing to be used. Okay. So now this is all intended to make things precise for you, so that we sort of have a precise setup. And I will not go into a sigma field again and try and sort of work with this abstract setup. So going forward, I will do the following. So going forward, we will do the following. So let's say we'll do the following. So we will restrict our sample space to be real numbers. So restrict sample space to subset of real numbers. Sample space to be real numbers, or subsets of real numbers. That's the only uncountable spaces I would consider. Sorry about the disconnection. So now what we'll do is we'll do this, and we'll also do one more thing. When I don't want to keep on doing Borel sigma field and all this stuff. What I'll do is when I say A is an event, we will also restrict ourselves to A being either an interval or finite / countable union of intervals. There's no off here. Intervals or complements. And that's all I will work with. I will not work with an average or a typical Borel sigma field event. I'll just assume that when I say event and I want to show something for an event, I'll just show it for an interval or a counter culture interval. I will not show it for any arbitrary Borel. That will require a far more theory than what the scope of this course is concerned. So whenever we want to show something for an event, whenever we want to prove something for an event, we'll only consider these guys. Very nice. I will not do any arbitrary collection. I'll just do this. Okay. So now, let me now go and get back to my original idea of trying to understand how do I pick a number uniformly in 0, 1. So that's something I have not done yet. I will close the lecture by completing that object. And one thing you'll notice is that even there, I will always work with S and R. Okay? I don't have to work with this. Even though I can work with a subset of R, I don't have to work. I will define probabilities on R, and the way I define my probability, it'll automatically give you appropriate experiments which are coming from subsets of R. Very good. This is something that. So now let me do this. Let me do 5.1.1. So to sort of understand how to do the following experiment of choosing number uniformly in 0, 1, I've told you, okay, this is what I mean by event space. I need this. Now I'll define what's called a probability densities of R. So the primary way to define a probability on R is to go through what's called a density function. That's the first step you understand. So the primary, there are other ways, but what's happened to my internet is gone again. Okay, very good. So the primary way of defining probabilities on R is via density function. So the primary way of defining the primary method of defining probabilities on R is via what's called a density function. I will illustrate that in the next step, in the example. So here's an example, example 5. So here the idea is the following, that what I'll do is, I'm going back to my experiment of choosing a number uniformly in 0, 1. Very good. So now what do I do here? I say let f be a function from the real line to the real line. I take a function f. The function will have two properties. One is it's going to be 1 in the interval 0, 1, and it's going to be 0 otherwise. That's my function. Is it clear? That's the function. So let me just draw a graph of the function. The function is on the x-axis like this. The points 0 and 1 are here. The function is just is 1 on the interval 0, 1 and 0 outside. That's how my function looks. Very good. Very nice. So now I have to do the following, that how to define probability. So now I take an event A, let A be an event. A be an event around. That is, A is part of the Borel sigma field. So, but as far as I'm concerned, I want to think of it as an interval. Then I define the probability of A to be equal to integral over A f of x dx. That's how I want to define it. So I define the probability of an event A as the integral of A over x. That's the definition. Now, of course, obviously, to understand this for an event A is quite easy, right? Let's see. So, example, if A was the event, let's say, A was the event, the interval, let's say 3 by 4 to, let's say, 1, then the probability of the interval 3 by 4 to 1 would be just the integral from 3 by 4 to 1 of f of x dx. But we know the function f is 1 in interval 0, 1. So we come down here, and that will imply the probability of 3/4 to 1 is equal to 3/4 to 1 times 1 dx. And that's just if you use a calculus, is just x, and I go from 3/4 to 1, and I get 1 minus 3/4, and that's just a quarter. Very nice. That's one example. Or another way you can think of it as, if you take the example A to be the interval, let's say AB, the interval AB, where A and B are between 0 and 1. Let's say, since I took strictly between 0 and 1, let me just go back here. Let me erase this a little bit. Very nice. So I take probability of the event AB. Like here, I just go A to B, f of x dx, and that's again equal to A to B, 1 dx, and that's the same as, because A and B are between 0 and 1, so therefore the density function is 1, and this is just going to be x from A to B, and that's just B minus A. Right. So by this definition of probability, that is the integral of f, where f is given by the top guy, I've achieved the following, that the probability of an interval in 0, 1 is equal to the length of the interval. Sorry about that, length of the interval. Well, this is one thing to achieve by this density function. And one can also check the following, that which we will do next time, is that let's call P defined by star is indeed a probability. Probability, we already verified that that probability interval in 0, 1 is length of the interval 0, 1. We'll have to sort of understand completely about why this connects to an experiment. We'll also show next time I'm sorry about that. Next time, the probability of a singleton set is 0. We'll also show that if A comma B is not contained in 0, 1, if A comma B is contained in, maybe the best word is A comma B is contained in A comma B is contained in 0, 1 complement, then probability of A comma B is 0. And once I show all these two things, then this will imply that P is a model for choosing a number uniformly in 0. Very good. So I'll just quickly recap the last 2 points. I'll close for the day. So the main idea was that I wanted to define a probability that will give me my experiment, that I choose a number uniformly in 0, 1. And the way we define probabilities is via a density function. And the density function, I didn't sort of define what density function was. I just said, let's take this function f, which is 1 on the interval 0, 1, 0 outside it. And so far, and I defined probability of A to be integral A f of x dx. And so far, it looks good. Of course, this may not be the correct answer, but I will show you that it is as we go along with this class. And this will indeed be the correct probability of choosing a number uniformly.